And now I will introduce the next speaker, who is Anthony Harris. Anthony is a researcher at the University of Queensland. He uses behavioral measurements, eye tracking, and EEG to study the influence of neural oscillations and aperiodic activity on perception and cognition. He joined the EEG Many-Lab initiative to replicate the work by Mathewson et al. 2009, and on the role of alpha phase in visual perception. And he will talk about this multi-lab collaborative project. Thank you, Anthony.
Thanks, Mara. So for those of you who aren't familiar, the EEG Many Labs project is a large-scale collaborative initiative to replicate 20 of the most highly cited EEG findings in the literature, with each of those findings being replicated both in experiment and analysis across at least 3 labs, in many cases more. And so as Marta said, today I'm going to tell you about our current progress in one of them. We're not finished, but I'll give you a little bit of data. And we can see where that's going. The focus is on how the phase of alpha oscillations measured with EEG impacts visual perception. So, as everyone in the room is familiar, I'm sure, EEG reflects changes in electrical activity measured from the scalp. And I have a mouse with a laser pointer. There we go. And as is often observed in EEG, you get these large bursts of rhythmic fluctuations that emerge in the data. They're high amplitude enough to observe with the naked eye, and typically around 10 hertz. These are the alpha oscillation for anyone who's not familiar. And decades of research have linked alpha oscillations and changes in their frequency, amplitude, and phase to fluctuations in perception, attention, working memory, and a range of other cognitive capacities. And this has led to theories of the role oscillations might play in coordinating neural activity to give rise to these aspects of cognition, such as the one shown here, suggesting that alpha oscillations might be a reflection of, or possibly a coordinator of, in a circular relationship, of cortical excitability, such that when alpha oscillations are of low amplitude, the excitability of the cortex doesn't change much, and cognition and perception don't change much over the alpha cycle. But when that amplitude grows large, then the cortex that is producing those oscillations is fluctuating through states of higher and lower excitability over time that we can potentially measure as impacts on perception. So these ideas, at least in the modern era, began with these 2 papers that came out in the same issue of Journal of Neuroscience in 2009 from Bush and colleagues and Mathewson and colleagues. They both tested the same idea: do alpha oscillations coordinate perception or predict perception? And they both found the same result, that stimuli that are very close to threshold are predicted, your likelihood of perceiving those stimuli is predicted by the phase of oscillations at the time the stimuli occur. This has driven a wealth of research, as well as I said, theories of how these oscillations might relate to organizing perception and cognition itself, how the brain might be instantiating these cognitive processes. But that's a very big idea, it's a very big claim, and so it needs to be based on solid research. And so in the Many Labs project that I'm going to describe today, we're performing a replication project of the Mathewson experiment. It's an exact replication, and I'll get into the details in just a moment. Starting with the paradigm and what they found, so you know what we're attempting to replicate, it's a very simple perception paradigm, a meta-contrast masking paradigm, where participants fixate in the center. They're presented with this target, which is a faint gray disk in the center of the display that is followed after a brief period by an annulus that is titrated to a level of contrast that results in a perception of this target on roughly 50% of trials. I think in their actual results it was closer to 70%. But what they observed in this first study was when you looked at the EEG related to these, focusing on the gray line first in the middle, that overall there was no particular rhythm present in the EEG. But when the data was split into detected trials where the stimulus was detected and trials in which it was not, they observed that at the time the stimulus occurred, there seemed to be a 10 hertz rhythm in that ERP that was at differing phase depending on whether you saw the stimulus or not. At a peak for trials in which the stimulus was not detected and a trough for trials in which it was. And so they sought to explore this result in a bit more depth to try and quantify this statistically. And they did so in 3 ways, which are the 3 tests that we're seeking to replicate in our replication project. The first is that they split the data. If you take your circular phase space of an oscillation cycling round and round, and they split that in half at the angles that are orthogonal to the average angle for the undetected trials. And they showed that if you take the detection rate in each of those bins, the putative good bin and the putative bad bin, when alpha oscillations were low in amplitude on the left here, there was no difference in the detection rate between those bins, as would be expected if the system isn't varying much as it cycles through that oscillation. But when alpha oscillations were of high amplitude, then the 2 different phase bins resulted in significantly different detection rates with more detection in the putatively good bin. Seeking to get more of a continuous measure, they then used a Hotelling's t-squared test. Wrong clicker, there we go. To quantify the difference between the average angles between those 2 bins. This is simply a multivariate t-test where they included the x and y values of the Cartesian version of the circular data. Which, as you can see, the average angles there for the undetected trials and the detected trials were roughly opposite. And then finally, the third result that we're attempting to replicate is that they found that if you took the trials binned into these 2 opposite phase bins that they observed, the N1 ERP component differed in magnitude between them. And so these were the findings that have then spurred a wealth of other research. And there have been a large number of studies that have replicated effects like this and like those of the Bush paper. This is just a sample here. Most of these are relatively similar in design, fairly homogeneous, but there is a growing number of null results in the literature in attempts to replicate these effects. These are far less homogeneous. There's a lot more variability in the designs, but nonetheless, there's a growing sense of, can we trust these particular results? And in particular, I want to highlight this paper from the organizers of this arm of the Many Labs project. This was a registered report project that was very similar to the design of the Matthewson study, and it didn't manage to replicate the phase result. So that sort of drove that was the impetus for the current project, which is to just aim to do an exact replication of the Matthewson study. And I'll explain that asterisk in just a moment. This is a registered report with stage 1 acceptance in principle at PCI registered reports. We had 9 labs collecting data on the project. 3 have completed, and I'll show you that data today. 6 are closer to completion, but it's been a difficult study to run, so it's taken longer than we expected. Each lab is collecting 35 complete data sets, replacing any exclusions. And this sample size was determined by taking the 3 original effects we were interested in, getting their effect sizes, halving them, estimating the number of participants we would need to have a 90% chance of observing those effects, and then taking the largest number, which was 35. So we should be well powered to reproduce the effects of the original paper. Now, the asterisk there on the word exact is that we do have 2 very minor differences to the Matthewson protocol. These were approved by the organizers, the original authors, so Matthewson and colleagues, as well as the organizers of the Many Labs project. And these are that we staircased performance In the original Matthewson task, they used one fixed contrast for every participant in the design that they had worked out through piloting would be the right one to produce the right level of performance. That's hard to do when you've got 9 labs with 9 different computers and 9 different set types of monitors all running the same task. So we elected to staircase performance. Participants come in. Let me show you here. They're given an example. They do some practice trials. We staircase them on the task to aim for 50% detection rate. And then we give them 72 validation trials to ensure that our staircasing worked. And if it didn't, we do it again. And then we test again, and if it still didn't, we kindly thank them for their time but exclude them from the task. And if the titration worked, they were within all of these inclusion criteria, then we prepare them for the EEG, take a resting state measure, and then they do 16 blocks of 72 trials each of the main task. The other difference was simply refresh rate of the monitor. Matthewson used a CRT with an 85 hertz refresh rate that's hard to come by now. So we allowed changes of refresh rate to be 100 hertz instead, producing a difference of a couple of milliseconds in a couple of the screen displays, but shouldn't have a major impact, especially as we titrated. So the paradigm as we used it is shown here, fits these timings. So in the original design, the target was present for 11.4 milliseconds. Here it's 10, no major difference. But otherwise, the design is the same. Participants shown this, the center stimulus, then the ring, and they simply need to say whether that center stimulus was present or absent. On 50% of trials, the stimulus and mask were present. On 25%, the stimulus alone, allowing us to make sure they're actually doing the task when they just see the stimulus with no masking. And on 25%, it was just the mask alone, allowing us to determine the false positive rate. And we aim to replicate those 3 main hypotheses of Matthewson that I described earlier. So that we would get, using a t-test, a significant difference in the detection rate between the 2 phase bins determined by Matthewson, that our Hotelling's t-squared would produce significant differences in the average phase for the 2 groups of trials, detected trials and undetected trials, characterized over the 200 milliseconds prior to stimulus occurrence, and exclusively at 10 hertz, and that we would observe the same N1 difference between the 2 phase bins that they determined. These are assessed separately for each lab, but most importantly, by meta-analysis across labs. And so as we're not finished with all the labs yet, I can't show you the meta-analysis results, but I'll show you the results from the 3 labs that have finished data collection. On the first hypothesis, none of the results were significant. So the t-test in the taking a median split on alpha amplitude, only analyzing high alpha for those 2 separate phase bins, there was no difference in detection rate between the groups. The Hotelling's test was significant in each case, and I'll come back to that in a moment. And the N1, likewise, non-significant. So a bit of a mixed bag here. We can't draw any conclusions from this. Part of the deal with the EEG many labs is that we won't draw any conclusions until we have all the data and we've done the meta-analysis. So I leave this for you. But I will note that we did include in the pre-registration that we would add some exploratory analyses, in particular adding some more modern phase analyses, because full credit to these authors, they were doing this for the very first time and making it up as they went along. They're doing their best, but these aren't the methods that are typically used today. So we will be reanalyzing this data with more modern methods. One thing that I want to note in exploring that hypothesis 2 result that was significant, this is the original Matthewson result that I showed you, where the point is that these arrows, being the mean directions in phase space for the 2 separate conditions, are pointed in completely opposite directions. What we observed for the 3 labs is not quite that. So each of these is one of the labs, and a dot is the colored dots are the mean directions, and you see that they're not strictly opposed. In one case, despite being significant with a Hotelling test, they are very nearly the same angle. And so this has led to some simulation work that we've been doing that suggested that perhaps the assumptions of the Hotellings test weren't quite met by this data. It assumes normally distributed data, and our data is not at the time of stimulus occurrence. And simulations suggest that that results in an extremely liberal test with about a 50% false positive rate. Hence the need for more modern analyses. So, I'm out of time. So some tentative conclusions. As of now, it seems some of the tests do indeed replicate, and the point of the project was to replicate them the way they were originally done. We've had a lot of debate about whether that is the right way to go about this, but that's the result as run. There are 6 labs to go. Data collection's been a bit rough. This is a difficult task to run with about a 50% attrition rate of participants whose performance don't meet inclusion criteria. Final conclusions are pending, as well as exploratory analyses. So I just want to finish up by thanking the organizers of this arm of the Many Labs project, as well as of the Many Labs project as a whole, and also the original authors of the work that we're attempting to replicate. They've been very forthcoming. They've shared all their code, all their old data. They've been very available to help design this project. Absolutely stellar academic conduct on their part. Big thanks to our labs and students, the people collecting all of the data, because it's been a lot of data. And to you, thank you for your attention.
Thank you, Anthony. Are there any questions from the audience? You can write them in the application, or you can talk on the microphone. Yeah? No, you have to go to the microphone.
Hello, thank you so much. That was super interesting.
Thank you.
I'm just wondering about your conclusion. So, stating that 1 out of the 3 analyses replicated, but the replicated effect, is it really a replicated effect given that the direction is different? So it seems like you're stating replication success off the significant p-values, but actually the direction is different. So I suppose my question is, how did you define replication success?
Yeah, it's a great question, and you've hit the nail on the head. In designing it without having collected any of the data yet, replication success was defined based on p-value, and that's part of the point. It's part of the struggle with these replication attempts, that how do you define it? How exactly the same does it need to be? And so that's really, I think, part of the takeaway here is that we've got to think very carefully about how we define a replication success and how we then interpret that, because I'm not allowed to interpret this. We haven't run the meta-analysis yet, but in an imaginary universe where I would say that, yes, the test replicated, but that doesn't mean the effect as we think of it had replicated. Yeah, great question.
Perfect, thank you.
Cheers.
I have a question about the experience that you had in the EG Many Labs, because I think that what is very interesting about this initiative is that it's a replication initiative. So the design are already defined by the previous paper. So can you comment on the ups and downs of this aspect?
Yeah, it creates some interesting situations, right? So Marta and I were talking before coming in here about the difficulties we've had with data collection, because if you're replicating an experiment, you can't change the task. You can't change it in any way. And so getting a few participants in and finding that we're having to reject literally 50% of our data. So my lab isn't finished yet because we need 35 data sets, and we've collected close to 70, and we're not there yet with successful data sets. And that's a real challenge. But I think it's unavoidable, is if in cases like this where the question is direct replication, it has to be direct replication. And that's just something to be aware of going in, I guess, that it could be a large challenge. Or perhaps collecting just behavioral pilot data to begin with to estimate how many data sets will be required might be a good way to go about things. I don't think there's necessarily any nuanced way around the problem, per se. Yeah.
Thank you. I think then we can move to the next presentation, which is me.